In this video, we're going to be doing complex zeros in the Fundamental Theorem of Algebra. And some of these theorems are going to sound familiar because we worked them with real zeros. So first off, the Fundamental Theorem of Algebra says this: a polynomial function of degree n, where n is greater than or equal to 0, has at least one zero in the complex number system. Now, we don't stress this enough. Sometimes we fail to tell you enough that a real number, any real number, is also a complex number. Complex numbers include all imaginaries, all reals. Complex numbers is pretty much every number that you've dealt with, including the imaginary. So if you have an n greater than or equal to 1, even if it's linear, you're going to have at least one zero in the complex number system. And you might be thinking, well, but I thought a zero was like an x-intercept where it crosses the x-axis, and it is. An x-intercept is a zero. However, there is a possibility that it's not going to cross, but you're still going to have imaginary zeros. So therefore, next up, linear factorization. This is something we've done with real numbers. We're just working it backwards. And now doing with complex numbers. If C is a complex zero, it can be imaginary, it can be real, it can be any of them, of a polynomial function, then x minus c is a linear factor of the polynomial. So this tells us that all polynomial functions can be completely factored, even down to linear factors. We don't have to leave any of them as x squared plus 5. We can factor even that down. So therefore, a reminder again, it says this. Example, if 3 is a root or 3 is an x-intercept, we know that x minus 3 is a factor. If 2 is a root, then x minus 2 is a factor. If I is a root, let's change it to that. What about the complex ones now? If I is a root, then x minus I is a factor. Okay, so now it says find all the zeros of the function, just like we've been doing. Then find the complete factorization. Break it down into completely all linear factors. So first off, let's find all of our zeros. And we can do this by simple factoring here. X squared times x squared, adds, multiplies would be a negative 25 and a positive 1. X squared minus 25, you can factor that again, or we can stop now and go ahead and set each of these equal to 0 since they're quadratic. Move the 25 over and take the square root. That's going to be plus and minus 5. Move the 1 over and take the square root. That's going to be plus and minus the square root of negative 1, which is I. Now that we know what our 4 zeros are, and again, we knew we were searching for 4. Now that we know what those 4 zeros are, we can now completely factor this function. We know that this function can be written as, our roots are 5, so therefore x minus 5 is a factor. Our root is negative 5, so that means that x plus 5 has to be a factor. Our next root is positive I. That means that x minus I is a factor, and negative I means that x plus I has to be a factor. So that's your complete factored form. All those are now linear factors. Next one, set it equal to 0. Let's find our 4 roots. 2 sets of parentheses. X squared times x squared gives you x to the 4th. Adds, multiplies will be a negative 6 and a positive 2. Set each of those equal to 0. X squared plus 2 is 0. Move the 6 over and take the square root. That's going to be plus and minus the square root of 6. Move the 2 over and take the square root. That's going to be plus and minus the square root of negative 2, which will be plus and minus I root 2. Therefore, our complete factored form, f of x is equal to, since your first root is root 6, that'd be x minus root 6. Since your next root is negative root 6, that'd be x plus root 6 would be a factor. Since your next root is positive I root 2, that means your factor would be x minus I root 2. And your last one is negative I root 2, so that means that x plus I root 2 will be a factor. Next one, we can use slip and slide on this, set it equal to 0. You now have 9. We're going to slip the 9. So it's going to be x to the fourth plus 35x squared minus 36. Factor normal. X squared times x squared adds, multiplies would be a positive 36 and a negative 1. We slip the 9, so now let's divide by it. And that's going to be x squared plus 4. And that will not divide, so let's try to reduce it. It won't reduce, so move the 9 back up front. Equal to 0. Set each factor equal to 0. Let's come over here and do it. So you have, zoom in just a bit, x squared plus 4 is equal to 0, or 9x squared minus 1 is equal to 0. Move the 4 over and plus and minus square root. That'd be plus and minus the square root of negative 4, which will be positive and negative. Square root of 2 times square root of negative 1 would be 2i. So there's 2 of your roots. Move the 1 and the 9 over. It gives you x squared equals 1/9. So that means that x is equal to plus and minus the square root of 1/9. You can split a square root, square at the top, square at the bottom gives you plus and minus 1/3. So therefore, your factors, you can now say f of x is equal to your factored linear factorization of this. Your first factor is 2i, so you have x minus 2i. Your second factor, positive 2i, would give you x, or negative 2i would give you x plus 2i. Since 1/3 is a factor, since 1/3 is a root, x minus 1/3 is a factor, and also x plus 1/3 would be as well. So if you were to multiply this back out, again, make sure that you know that it would turn into that. Okay, number 4, finding our roots. Again, if you were to move this 81 over and take the fourth root, that would only give you positive 3 and negative 3. So that's not going to give you all the answers. So to get all your real and imaginary answers, or real, all the complex answers, you do have to factor it down to quadratic. So this is difference of squares. Difference of squares factors into conjugates. X squared times itself gives you x to the fourth. 9 times itself gives you 81. Since it is now quadratic, you can now stop, set each factor equal to 0. And that's going to give you, move the 9 over and take the plus and minus square root of negative 9, and that would give you a 3i. And here, move the 9 over and take the plus and minus square root of 9, that gives you 3. So there are your 4 roots. So therefore, your factored form would be f of x is equal to x minus 3i and x plus 3i for these 2 roots, and x minus 3 and x plus 3 for these 2 roots. Number 5, factoring by grouping. Group the first 2, last 2. We're setting it equal to 0. Now gives you x squared times x minus 5 and a positive 16 times x minus 5. Factor in x minus 5 out of both groups, and you're left with an x squared and a plus 16. Now that it's linear and quadratic, we can set each factor equal to 0. And you'll get that x is either equal to 5, or move the 16 over and take the square root, and you get x is equal to plus and minus the square root of negative 16, which you can split into the square root of 16 times square root of negative 1, which gives you 4i. So there's your other 2 roots. So therefore, factored form would be f of x is equal to x minus 5. And we're just getting practice seeing the connections between factors and roots here is the only reason we're asking you to do this. X minus 4i and x plus 4i. Because in the next section, you're going to be working these problems backwards. You're going to be given roots, and you're going to ask to find the factored form. Next one, again, factoring by grouping, set it equal to 0. Pull out an x squared, you're left with x plus 6. Pull out a, and it doesn't look like this is going to work, pull out a negative 2, and you're left with x 7x minus 8. Notice that the what's in parentheses is not the same, so therefore we're going to have to try a different method here. So if factoring by grouping doesn't work, we're going to have to try to list our possible rational roots and use some synthetic substitution here. So let's list all of our possible rational roots. And there they are. That was all the factors of 16 over all the factors of 1. And it gave you these 10 possible rational roots. Start since that synthetic substitution, plugging in until you find one that works. So here you see where I've used negative 8 to divide by. So I divided by a factor of x plus 8, and I came out with a remainder of 0. So therefore, I've now rewritten my function as x plus 8 times this, which would be x squared minus 2x plus 2, which is not factorable. But we can stop and set each factor equal to 0. So I have x plus 8 is 0. Give me x is negative 8. So we'll go ahead and solve that. And then x squared minus 2x plus 2 is equal to 0. And you can solve that by by quadratic formula or completing the square. Since we use completing the square last, we'll use some quadratic formula. Let's work our discriminant first. B squared minus 4ac, a is 1, b is negative 2, and c is 2. So b squared will be, let me write that down, b squared minus 4ac. B squared would be 4 minus 4 times 1 times 2 would be 8. That'd be a negative 4. And again, that's going to be under your radical. So that will be a 2i. So now let's plug in the rest. And I think we can just come over here and do it. So our x values will be negative b plus and minus that over 2 times a, which would be 2 times 1, which is 2. So that's going to be when you distribute your 2, 2 divided by 2 plus and minus 2i divided by 2. There's your other two roots. So now this one's going to look a little bit different. So our function written with just the roots would be, since x equals negative 8 was a root, that'd be x plus 8 will be a factor. And here's how we're going to write this. Since 1 plus I and 1 minus I are your other roots, you really need to leave those in parentheses. So x minus, since 1 plus I was a root, then x minus 1 plus I will be a factor. And since the other one was 1 minus I, then x minus 1 minus I is going to be a factor. So there's your factored form. Number 7. This one, we can't factor it. This is not even powers and half powers and all that, so we can't use what adds and what multiplies. So let's go straight into finding our possible rational roots. And there they are. And let's go through and start trying to find something that gives us a remainder of 0. So here we divided by x plus 4 and got a remainder of 0. So that means that x plus 4 is a factor. It means that negative 4 is a root. So we can actually rewrite our function now. So our function is equal to x plus 4 times constant x squared. That'd be x squared minus 4x plus 5. X squared minus 4x plus 5. We now are going to set equal to 0. Set each of our factors equal to 0. So I'm going to get x is either equal to negative 4, or let's come over to the side and we'll complete the square this time, because our b term there is even and we don't have to factor anything out, so that's fine. Pretty easy to complete the square here. X squared minus 4x, move the 5 over. Take your b term, half it, square it, add it to both sides. So we're adding 4 to both sides. Next will always be to factor. Perfect square, this factors into x minus 2 squared equals negative 1. To undo a square, we're now going to move the square over by doing the plus and minus square root of negative 1, which we know is I. Now move the 2 over and you get your other two roots are, put the 2 first, 2 plus and minus I. So therefore the completely factored form of my function, since negative 4 is a root, that would be x plus 4 is a factor. And then since 2 plus I is a root, that means that x minus 2 plus I is a factor. And since 2 minus I is a root, that means x minus 2 minus I must be a factor.